Hey everyone, we are DropLab, and today we're going to talk to you about what we do at DropLab. So at DropLab, we're making a low-cost lab-on-chip device called Digital Microfluidics, and in short, DMF. So basically, DMF works on the principle of electroweddings, in which we can actuate droplets on electrodes by applying electric field. So the main advantage of DMFs over traditional microfluidics is that it is programmable, meaning that we can use machine learning such as Bayesian algorithm to automate the experiments and also analyze the experiments and find an optimal parameters and find the ideal procedures in real time. And with our system, we can actually design, execute, and analyze results with minimal human interference. So how does it actually work? So the DMF structure, as you can see on the figure on the left, has two electrodes that are coated with hydrophobic layers, and the bottom one is also more of a hydrophobic and a dielectric layers. So the top electrode is also ITO, that is conductive, and also coated with hydrophobic only hydrophobic layers such as Teflon. So by applying an electric field to the electrodes, we can reduce the contact angle based on the equation on the left side. So if you apply voltage to the electrodes, you reduce the contact angle. By reducing the contact angle of the drop, you can see the figures on the right. The drops will, like the contact angle of the drop will decreases, making the drop flattens out, and that will make it to reach out to a neighboring electrodes. So in order to move the drop, you turn on the first electrode and then turn on the other electrodes really fast, such that the drop just gets pulled. The figures on the graph on the bottom right shows exactly how it works. So for the hardware so our project consists of three components: materials, and hardware and software. So one of the main hardware is switching boards. But before I go into that, I would like to tell you that we made requirements for us to actually achieve is that we have to have safety for our device. So safety is as a crucial factor. We have to make sure that our device is not harmful to the user because we plan to eventually sell the products to customers. And also we want to make our system modular design so that if something happens to the system or you want to add anything, you can only swap one component at a time. You don't need to rebuild the whole system. And also for us, since we need to actually get results, we need to do a rapid prototyping for our projects. So this is like a main thing for hardware is that we had to buy equipment to help us to rapidly prototype our devices. So we targeted to have a low-cost product to allow it to make it available to everyone. And also, this is the most important thing with this is high accuracy and versatility because we want to make sure that we are able to run many experiments in many different fields, from chemistry, biochemistry, and others. So one of the main boards from the hardware section is the switching board. So switching board uses a chip called shift register, HV507. Basically, it's a chip that controls selectively or independently each electrode. So this chip is rated for high voltages, and for our projects, we need high voltage AC. So for that, we're using, so this chip it requires AC voltage, but the AC voltage cannot pass through because this chip only allows positive voltages. So in order to avoid this, we had to offset the AC voltage above zero. So it counts from only positive values. So the DC offset will provide enough voltage to offset the AC voltage to pass through the shift register. And then after the shift registers, it goes through the capacitor that we call decoupling capacitor to remove this offset and only provide the AC to the electrodes. So we're using a flex cable for connectivity because it's really robust and really accessible and inexpensive as well. So beside the shift switching board is that we need to provide this power supply. So we made our power supply components, and it consists of two main things. We have the AC components and the DC components because, as I said, we need the AC component, the voltage, for our application, but we need the DC to provide the offset. So for the AC, because most of the function generators exist in the market, goes up to like 30 volts for like, 30 volt peak to peak. So in that case, we had to use transformer as a step-up voltage to increase the voltage up to 200, from 80 to 100 volts peak to peak. So we went through like a lot of iterations to find the optimal or the best way to amplify an AC signal. We tried op-amp, we tried transistors, but we found that transformer worked the best. To provide the DC offset, we built a DC booster that provides like from 12 volts up to 270 volts, and that will ensure that we have exact enough voltage to operate the chip. So when it comes down, once we have the power supply on, once we can control the electrodes through the switching board, now we can connect them to the electrode board where we have, like as you saw at the beginning, where you have the drops and you can move the drops on that that board. So we have done work with as a collaboration at U of T, a group at U of T, that they microfabricate the chip. So microfabrication is a great way to actually make this kind of chips, but normally they're really expensive and it's not accessible as PCBs. So we went with PCBs because accessible, but also it's really low cost. A chip like this costs about 50 cents to make. So with this, since it's really inexpensive, we can actually make a lot of it and actually increase the number of electrodes on it to allow people to actually be able to run multiple experiments at the same time on the same board. So we have an issue. We encountered an issue when we ordered the PCBs from China. Is that some of the board has non-uniform copper layer. So with that, we had to do like some mechanical polishing. We ordered the chips to have a solder mask on top, and then we polished that to make a uniform film, and we actually got a nice result.
The surface. Yeah.
So with that, after we had this nice result, the reason actually we want a uniform film is that when we apply a hydrophobic layer on top, we want to make sure that the hydrophobic layer is uniform on across the board. Because if the film is not uniform, applying voltage in one area will require higher voltage than the others. So that's a critical part for us. So we have to make sure it's uniform.
So
Actually be able.
Sorry. So yeah, I'll be talking about the software component. Okay, I'll just hold this. Okay. So. Oh, okay. Anyways, so to begin with, our primary software requirements was to essentially avoid any learning curve to the users. We wanted to make it simple, where they can focus on their experiment and not on a lot of the commonalities that come with complex software the complexities. And we also wanted to make our software parallelizable so that people could execute not only once they execute a single experiment, they would be able to massively execute the experiment on the same board. So essentially, to avoid improve performance, etc. So to begin with, the first component is our user interface. We made it work to run in the web browser, and the application actually runs as like a local web server, and this allows it to be cross-platform, so it runs Windows, Mac, and it's not dependent on your hardware. We also try to make it flexible, so we have a layout system so that users can add their own extensions, and it's really easy to build. Everything is just written in JavaScript and is plug and play. With the electrodes, you can directly control them and even operate them without being plugged into the hardware, so you can write recipes while you're away. And the final component of the user interface was also the loading and saving of previous recipes. So this is just the interface for essentially a REST API that I'll be using in the other parts that I'll be showing later. But this is the general control that you have, and you can interface with it directly, or you can using the REST API that I'll be showing later. So on the back end, we use WebSockets to communicate to the Arduino. And so that talks to the shift register and tells you which electrodes to put at high voltage or low voltage, etc. With feedback between the two. So if things go wrong, you can go back to the front end and alert the user. And now in terms of experiment parallelization. So We implemented at first a cooperative pathfinding system, but we found that this system wasn't really stable. There was often failures. And so we moved towards a traffic control system used in a lot of other areas of automation. And now the traffic control system has nodes of selective rules. So there's certain electrodes act as highways, certain electrodes act as parking spots, and certain electrodes are for sensing and for mixing, etc. And now when we combine this, we could actually, as you can see here, we can avoid collisions, and you can run the experiment once and then start a new node and then run it again and again. And then you just add the module over and over again, and now you can run the same experiment 1,000 times. So it's incredibly parallelizable that way. And now also, when these get large, of course, creating these rules can be time consuming because each individual node has directions. And so to avoid this, physics engine, 2D physics engine was implemented using raycasting to actually generate the node rules without the user having to do it. So all they have to do is upload their PCB design, and it'll auto-generate the highway system that they're using for the traffic controller. So then this makes it incredibly easy. You just upload your design, and it's ready to go. With just a few comments that you can make on your polygons in your device design.
Thank you. I will be talking about the rest of the project. So as Abdullah mentioned, the device consists of a PCB substrate with an ITO glass on top, and there's a dielectric layer that ensures that we have a large capacitance between the droplet and the bottom layer. So to get this dielectric, there were some criteria that we had to keep in mind. Firstly, it had to have great electrical properties. That means that it had to have high dielectric strength and high dielectric constant, meaning that it shouldn't break down at the high voltages that we were applying to get the actuation. Second, we needed to apply hydrophobic coating to increase the contact angle and make it easier for the droplet to move. This was usually done by applying a Teflon coating on top, which we will talk about later. Lastly, it was very important for us to have a simple fabrication method that would allow us to use the resources that were available to us to fabricate our chips. So there were three main options that we considered. Firstly, Parylene C and Teflon AF, which are most commonly used by people in the field, were considered. But the problem with that option is that Parylene C is very hard to deposit, and as it needs a CVD chamber to be able to be deposited. This is often not available at most places because Parylene contaminates the chamber and makes it unusable by other users. So the only place we found that was willing to let us use their device was a place at U of T that wanted to charge $300 for 10 samples, which is not terrible, but as we'll talk later, we found better options. And also Teflon AF is very expensive. The second option we considered was a Capstone FN film. Capstone FN is made of polyamides and has excellent dielectric properties and is extremely cheap. It also comes with a layer of Teflon, FEP Teflon already coated on one side, which reduces the need of applying hydrophobic coating on top. But the problem with that is that we had some trouble getting the film to stick to our surfaces, which created an air gap, which reduced the electrical properties that we wanted. Lastly, we went with Cytop, which is a dielectric material that has excellent dielectric properties similar to Parylene, and is actually hydrophobic itself, so we don't have to apply Teflon. This helps. We can also spin coat this onto our PCBs, which is the best option we wanted. So some of the applications that this device could have, I will be discussing. Firstly is biosensor fabrication and testing. We've been working with a group in Kitchener called Medela Health that creates glucose sensors. We've been working to automate some of their processes for biosensor fabrication. This device that you can see here, can't see here, that one is the holder that we designed for them. So they would be fabricating 4-inch glass wafers with platinum electrodes etched onto them, and they would provide us with active material that we would deposit onto the electrodes. We will then do an electrical or optical readout of the sensors and optimize for sensitivity and accuracy. Since our device is completely programmable, we can use iterative design and implement Bayesian learning, which would help us learn much, much faster than a researcher in the lab. Okay. There are some possible other avenues that we explored, such as cell culture growth, CRISPR, personalized medicine, metabolomics, and sample preparation for other microfluidic devices. Here I'll be discussing the further work that we'll be doing. Some of this is already underway. First is sensor integration. We worked to incorporate a spectrometer into our system and perform reflection mode spectroscopy, in addition to electrochemical sensing. Abdullah has done most of the work for that. Lastly, it is important for us to have a closed loop control system to ensure that the droplets do what we want them to do. Here we have the design that we have made so far. This is obviously a preliminary design. It consists of a few AT-Tinies, which are small microcontrollers that cost about 80 cents. These are then connected to a series of multiplexers that point these AT-Tinies to different electrodes. These AT-Tinies can measure the frequency of the resonance frequency of these electrodes and estimate the capacitance, telling us if the droplet is there or not. Then these multiplexers are themselves connected to shift registers, which we can daisy chain, making this design modular itself, meaning that we can connect multiple of these as we expand our board to make sure the user can easily expand the scope of their experiment. That is all. Thank you very much for your time.
Okay, so any questions? Got one to start.
Have you made it work?
Yes, we have made it work. We have not obviously implemented the closed loop control yes. We have not implemented the closed loop control. We have gotten the droplets to actuate.
Yeah. The video is like at first part, the Jeff has shown the droplets movement.
So which one is yours?
Not the colored one.
No, it's
No,
not
the colored one is not
I
ours.
didn't have it. No, I didn't have it.
I'm thinking that you show me a video.
Yeah.
You do the droplet run.
Yeah. Actually, it's like by the boost.
Yeah,
boost
if you're kind enough to come to our poster, there's a video. Yeah. Unfortunately, we were not able to bring your live demo because it broke yesterday.
Okay, but you haven't had time to do anything with applications, but can
Yes.
you say that you have the basic operations now?
Yes.
Yes.
Okay. And-
Well, we had the basics operations functional 2 days ago.
Okay. Video.
Yes.
And we
We do have videos.
Yes.
Okay, and then
Yes.
the software side of it, is that operational?
Yeah, I need to clean it up a bit because it was always fast-paced. But
Okay, so apart from a calamity, you think you're set to
Yes.
Yes.
start developing applications?
Yes.
Yes.
That's quite impressive. You've got some rough edges, but impressive work.
Thank you.
Yeah, thank
Any
you.
other questions?
It's a lot of work putting
Yeah,
together.
you
Yes.
put a lot.
We did. We put a lot of time into this.
It kind of came at the cost of the presentation quality, but
You're not supposed to say that. It's a bad
okay,
idea.
I didn't say that. I didn't say that.
Okay, but I recognize the challenges, quite a number of challenges within to be dealt with quite nicely. So, nice work. And, we found our next group. Good.
All right.
Perfect.
Thank you so much.
Yeah, thank you.
Okay, cheers.